Hello, everyone. Good morning. I hope that you had a nice day yesterday, if you were here, or a nice evening, if you were there as well. And I hope that you are very well rested today, because we are going to start the day with a conference about two things, or three, that are very much of current relevance. Performance, as well as cost, and cloud. Those are things we all care about, right? Unless we don't have budget limits, but that's another subject. So what about presenting you something that helps you reduce by a factor of, let's say, 15 times latency, and also divide by a lot the cost? That will be amazing, right? So the first speaker of today is someone that has been working at Google for several years and has been programming in Go for a decade. So I'm going to ask you for a round of applause for the first speaker of today, presenting towards modern development of cloud application. Please welcome Valentin Deleplace.
Thank you, Hugo. Good morning. There are so many of you. I'm thrilled. We'll have a good time today. So, today, I'm going to talk about Service Weaver, a new open source programming framework from Google for writing distributed application. So this talk is not primarily about reducing cost or getting super high performance. It's mostly about how to structure and distribute microservices. My name is Valentin Deleplace. I'm a developer advocate for Google Cloud. You can find me on some social media like Mastodon and X. And my pet projects are programmingidioms.org and coolmaze.io. You might want to check those out. These slides have been written by the Service Weaver team of software engineers, Robert, Michael, and Serjan. Thanks to them. So, microservices are becoming increasingly popular. This is a Google Trends graph that shows queries for the term microservices. The tooling around writing microservices is becoming more popular and ubiquitous. Docker and Kubernetes are almost synonymous now with microservices. Things like Istio, Argo, Prometheus are becoming increasingly popular as well. So there is no questioning that microservices are here, but it's unclear if they are universally good. In order to get a sense of what the developer community thinks about microservices, we sampled a number of comments from Hacker News. The first person says, "I don't like microservices, they are the worst of the worst." The second person says, "They aren't inherently bad, but they might be, but the way we are doing them is bad. We can do them too small, or the boundaries are misdrawn." The third person doesn't like monolith. It's a disaster, we are doomed, etc. The first person says microservices are not bad, and when people say they are bad, they use strawman arguments to say they are stupid. And the fifth person is unsure if they are writing a monolith or a microservice. Okay. Things get even more complicated when you look at messaging coming from larger companies. Uber, Etsy, and AWS have always said that microservices are great, but then AWS recently published an article where they stated that they saved 90% costs by switching to a monolith. So overall, there's no question that microservices are popular, but the jury is still out whether they are a good thing or a bad thing universally. We believe there are three fundamental reasons why there is so much confusion about whether microservices are good or bad. First, there is no official guidance or standard best practices for how to write distributed applications. Should you start with a monolith and keep it for it as long as possible until you know for sure you have to split? Or should you split early and often, just in case, because it can be way harder to split later? The second thing is that we don't live in this clear black and white world where microservices and monoliths are good or bad. They exist in a vast trade-off space that trades off things like ease of development, ease of deployment, testing, etc. In order to pick the right architecture, you have to understand this trade-off space and where your application fits in this trade-off space, which is extremely challenging. There are so many technologies out there that as soon as you finally understand how to use one, the other one is released that claims to be better. We also often make decisions based on bias that are not the most technically sound. For example, when you see companies like Google, Amazon, Etsy use microservices, you think to yourself, oh, I should also be using microservices, without thinking about why they made those decisions and whether they apply to you. We have found out that for these reasons, most people are just encouraged to split as much as possible without thinking whether splitting makes sense. As a result, they end up with a complex system with n different binary configs, all being released on a different schedule. Conversely, people have had bad experiences with some of the earlier frameworks, and as a result, they stay away from frameworks because they have fundamental problems. I had bad experience with Corba, and as a result, I stay completely away from frameworks that aim to be helpful by hiding the network, for example. Based on these observations, we also based on our own experience developing distributed applications, we came up with 3 core ideas as a solution to these challenges. First, we believe that applications should be written as a logical monolith, compiled into a single binary. But then it should be deployed physically as a set of microservices. In other words, we want to decouple logical and physical boundaries of your application. This allows you to change the physical topology of your application easily and on the fly. Second, you should delay the decision of using a microservice or a monolith for as long as possible. Today, people have to sit down and make a decision upfront about whether they are writing a monolith or a microservice. We believe that they should start writing their application code and make this decision later, once they have the experience and knowledge to know what's best. Last but not least, ideally, the developer should focus on the app business logic and offload the complexity of cloud interactions to the runtime. We have to make opinionated choices about which underlying technologies to use for which use case. Otherwise, the user would have by themselves to choose along this trade-off solution matrix, which is a difficult task. These ideas sound great, but how do you implement that? That's what Service Weaver does. Service Weaver is a framework for writing better microservice applications that make it easy to develop the application, easy to deploy it, and easy to maintain it. And as important features, we want high performance, multi-cloud support, and reduced cloud costs. Where am I? In this talk, I will dive into the details on how to do this. The talk has 4 parts. First, we will show how the user develops their application using Service Weaver. the user writes a logical monolith using only native programming language features and without worrying about code versioning. That's important because code versioning is quite challenging. Second, once they have written their application, how do they deploy it? Even though they write a logical monolith, the runtime will rip the binary apart and deploy it as a set of microservices. You can run it without changes locally or on Kubernetes or on a specific Kubernetes runtime like Google Cloud GK. Third, our runtime is optimized for efficiency. And fourth, we provide tools for debugging, testing, observability. That is very exciting. Let's go into the details and find out how to develop with Service Weaver. Just a quick pause. A Service Weaver application consists of a set of components that call each other, where a component is somewhat similar to an actor, if you're familiar with the actor model. Under the hood, Service Weaver uses a code generator to weavify the application. For example, to generate encoding, stubs, registration. So as a reminder, Go is a compiled language, statically typed, and it is sometimes useful to resort to code generation that is much more efficient than, for example, using reflect everywhere. To write a Service Weaver application, we write a modular binary, and then we can deploy it on our laptop, where components can run in the same process, or multiple processes, and then we can run it distributed on different machines, on pods that can be replicated, and traffic load balanced between replicas, etc. When I say monolith, I don't mean deployed to a single machine. Of course, you can have a monolith that is deployed and replicated on many instances. The real difference is, does the monolith contain the whole application or just a few components? So how does a developer write a Service Weaver application? To define a component, we define a Go interface. Is it too small, or can you read? Yes? OK. Here we define a cache component with a put method, and we can have other methods as well. Next, to implement the component, we write a Go struct. That is the concrete implementation, except that we have to add a weaver.implements embedding. That is somewhat specific to the Go language, what embeddings are, but it's nice just to know that's how we write it in the Service Weaver framework. To instantiate a Service Weaver app, in the main component, we use weaver.ref. And to run the app, we call weaver.run. Finally, we interact with the component with method calls. To deploy a Service Weaver application, we release a single binary along with a tiny config. We only have to specify the name of the application binary. And once we write this tiny config, we can execute go run on our laptop to run the application in a single process. Or we can call weaver multi-deploy to run the application locally, but in multiple processes. So multiple processes is useful even locally to simulate a distributed environment. Otherwise, when they run all in the same PID, then you don't have exactly the same behavior in theory. If we want to deploy in a distributed environment, we can add per deployment information in the config file. For example, to run on multiple machines via SSH, we need to specify a file that contains the names of the machines. Then we run weaver SSH deploy to run the same application binary that we run locally, but on multiple machines instead. If we want to run on Kubernetes, we can run weaver kube deploy to generate the Kubernetes deployment for the application. And then using the kubectl command, we can deploy the application in any Kubernetes environment. That can be GKE, EKS, AKS, etc. We also have a custom GKE deployer, Google Kubernetes Engine, that enables deployments across multiple regions, safe rollouts, routing, and can do custom resource management. The nice thing about this deployer is that it is highly customizable with various knobs that user may want to control. Let's look a little bit in more details how a Service Weaver application is deployed. As mentioned, we write the application as a modular binary that consists of a set of components, for example, rock, paper, scissors. Service Weaver will place these components in two processes. By default, it places each component in a different process. However, if you specify any collocation in the config, then Service Weaver will respect those policies. Next, Service Weaver will attach corresponding libraries to the application that are responsible to manage the interaction between the application and the runtime environment. Finally, Service Weaver runtime can have different implementations. For now, we have deployers for the local machine, for a cluster of machines, and for Kubernetes environments. That can be GKE, etc., or also on-prem. You can have on-prem Kubernetes. Let's talk about performance. Service Weaver provides a highly efficient runtime that enables high performance and reduced cloud costs. It provides an efficient encoding-decoding mechanism that has no versioning overheads. It uses an efficient transport protocol built on top of TCP that embeds custom load balancing. It provides collocation that enables flexibility on how components are collocated. For example, chatty components that interact a lot with each other can be placed together in the same process, and they can use local method code to interact with each other. So transparently, you don't need to see it, or you don't need to specify it in your code, but instead of doing some network remote procedure calls, it will just do a local method call, but that's transparent. Finally, Service Weaver provides routing that helps to balance the load across multiple component replicas and also increases the cache hit ratio in case you want to collocate caches with your components for performance reasons. We benchmarked a popular application called Online Boutique that contains 11 microservices. We ran the application using the GKE deployer and compared the performance using the microservices version of the app and the Weaver version of the app. Our results show that with Service Weaver, you write less code into your application. This is because you don't have to write boilerplate code related to encoding, decoding, service discovery, defining proto buffers, integration with the cloud provider, and so on. Also, with Service Weaver, you write a tiny config file, while if you deploy as microservices, there are many configurations, and they are very complicated YAML files. In terms of cost, Service Weaver uses 10x less CPUs and improves the application latency by up to 37x. That is not 37%. That is really 37 times as fast. That's huge. Like all benchmarks, I would recommend to take the numbers with a grain of salt. The important thing is that you can get high performance with Service Weaver. It is designed to be performant. Finally, let's briefly talk about telemetry and testing. Service Weaver provides integrated logging. With Service Weaver, each component comes with an associated logger, and it's straightforward to log and to manipulate logs. Also, it provides metrics like counters, gauges, and histograms. One interesting observation is that Service Weaver generates some metrics by default for each application. For example, metrics that capture the throughput and the latency between various components. For tracing, Service Weaver relies on open telemetry. And to enable tracing, we have to create an hotel handler in the main function. Once tracing is enabled, Service Weaver will trace for us all HTTP requests and component method calls. Finally, Service Weaver allows us, with a single command Weaver GKE profile, to capture the performance of the application as a whole by profiling each individual process and aggregating into a single profile. Also, it provides metrics like counter, gauges, and histograms. One interesting observation, no, I've already said that. The throughput, yes, and the latency, already said that. For tracing, okay, I see what's happening. So I'll switch to a demo to see how Service Weaver actually works from the point of view of a developer. If my eyes are good enough, I will be able to code directly on the big screen. So I have a folder that is empty, and from scratch, I will code, define, and implement a Service Weaver component and an application. So first, I would need to initialize a Go module. Go mod init, I will call it reverser. Why reverser? Because we will be reversing strings. As we all know, reversing strings is the cornerstone component that allows companies to make a lot of money and to become unicorns. So we'll be reversing strings today. Let's create files, reverser.go and main.go, sorry. And main.go, okay, and I'll be opening VS Code to actually write the code. So for simplicity, we'll be in package main today. And in order to define a new component in Service Weaver, I define the new type reverser with a capital R, that is an exported type. In Go, if it starts with a capital, with a big letter, it means it's exported. It's like a public type. That's an interface. Interface contains methods, and what will our methods do? Reverse. It's taking a string, and it's returning a string. So this is the contract of my component. It says it's supposed to be able to reverse a string. However, it is not complete in order to make it a Service Weaver component, because Service Weaver components can be collocated, but they can also be on different machines. So when they call each other, they do actually network calls. So it's useful and mandatory actually to pass a context as a first argument of the component method. And because networks are not perfect, there are fallacies, etc. They are not always reliable. We might end up with a network error. So we need to, in the signature of the method, in the component interface, to return an error as a last return parameter. Okay, so I've defined abstractly my component. Now I can implement it with a concrete implementation that is a struct. I call it reverser, but this time not exported. I don't need to export the concrete type. It is a struct, and it will implement the aforementioned interface. We need to say it embeds weaver.implements, and because Go has generics now, we leverage and sometimes abuse the generics typing system to say that it implements our interface reverser. Okay, so now we've defined the component type, we've defined the concrete implementation type, but we need to actually implement the method. So it's not type, it's function. We take a receiver of type reverser. Reverse, so as I said, it's taking a context. Okay, it's taking a string S. It's returning a string that is the reversed string, of course, and an error. Let's see. In Go, all strings are assumed to be encoded in UTF-8. Can I just take the bytes and reverse the order of the bytes to reverse the string? The answer is no, that doesn't work. We need to work at the character level, and in Go, the character is called a rune. So first, I will convert my string into a slice of runes. Okay. Then, when my colleagues do this talk, they do a fancy loop in which they reverse the order of the runes one by one. But I'm lazy. I prefer to call slices.reverse because the package slices was added to the standard library in Go 1.21 2 months ago. I'll just use that. Slices.reverse runes. Okay. Now I need to convert that again into a string. I will return the reverse string and an error that will be nil because I didn't encounter any error just by doing some runes manipulation in memory. Okay, that should work. So I define my component and the concrete implementation. Let's write an app that will leverage this component. So I'm in the package main, not with our demo, main. Obviously, there will be a main function. Just before the main function, I will define a type that is the type of my application. It embeds wither.implements. Is it implements? Yes, implements wither.main. Okay, that says this is a main component in Service Wither, a program that can be called. And my app will contain a reverser, an instance of the reverser component. So should it be the concrete implementation, or should it be just the interface of the component? Actually, it's something else. It's a wither.ref. Why a ref? Because the main component and the reverser component might or might not be collocated. So it might have to resort to network calls, and so we use a reference that will take care for us of calling the component even if it's remotely. Okay, so in function main, we call wither.run. That's where I would qualify what I will write of a little bit of boilerplate. It's hard to come up with a perfectly nice syntax to do that. In this case, there is some boilerplate that I will be happy to type for you. So wither.run takes a context. By default, we pass context background, okay? And then it takes a function that itself takes a context. That's a little bit verbose because in reality, it will be the same value as the above one. So my function takes a context as a parameter and a pointer to the app, and it returns an error. Okay. Now that I've defined, that I've written this boilerplate, I can actually write the business logic of what my application is supposed to do. So let's say I have a string bonjour. I will try to reverse it with my component, reverser. So I call app.reverser. This is a ref. This is not the real reverser. To get the real reverser, I need to call get. Okay. And then I calculate the method of my component. The method is called reverse. It's taking my context, it's taking my string, and it will return another string and an error. I have to check the error. That's how we do it in Go. Okay, not nil, return R. Okay. If no error occurred, I will print on the standard output the value. So let's do it nicely with printf. Let's say the original string reversed is my result string and a new line. Okay, original string, new string. Still have to type properly. Okay, that looks nice. I should be able to just run this application with go run. Oh yes, I need to return explicitly an error value, nil, when everything goes is fine. Will it work from the first time? I don't think so, but let's try. No required module. Okay, you need to go mod tidy in order to properly import the packages of Service Weaver. Here we go. Go run dot. Will it work? Let's see. Oh, it's doing something. So we have an app that is running. We have a deployment with some kind of deployment ID. And I would not call it a success because it does not seem to have reversed a string and printed out a string. Let's see what happens with Weaver. So yes, I installed the Weaver executable. That's part of the framework. And now that it's supposed to be... okay, I know what's wrong. Weaver.run returns itself an error. Yes. And so I'd better get the error and see and fail like log.fatal if anything went wrong. Maybe something went wrong. Aha, I have a message. Component implementation main.app not found. Maybe you forgot to run Weaver generate because it's supposed to be generating some code before running properly. You know what? Maybe I forgot to run Weaver generate. Let's do this. So it has generated for me a nice file, weaver_gen.go, that contains fascinating 300 lines of boilerplate that I don't have to write myself. That's pretty cool. Okay, let's see if it helped. Will it work this time? I hope so. This is my demo. I have pressure here that will require some kind of uploading if it works. Bonjour reversed is Ruojnob. Ruojnob, yes. Thank you. That is a $1 billion use case. We will all get rich with that business logic. Very cool. So that is a command line application with a single component running locally on my laptop using Service Weaver. Nice. Usually we prefer, Service Weaver is mostly suited to design web servers or any kind of server. So let's implement this service as an HTTP server instead of a command line application. We still need weaver.run with a background, with a boilerplate function definition. But here we will define a handler, http.handlefunc. For this, we just use the standard library, nothing fancy. The pattern is just slash. The handler, it's a function. If you've already implemented a server in Go, you know what it looks like. It takes a response writer and a request as a parameter. And here is where we implement the logic of handling the request. So the value will be passed as a request parameter, so r.formValue. Okay, we can put it as a query string at the end of the URL. It will be called S. Then I will cut and paste my business logic of reversing the string here. Okay, in case something goes wrong, I cannot return anything from the handler, so I have to http.error with my response writer, with the error string, and with some kind of HTTP code. Let's say, yeah, status internal server error should be fine, and we return. And then we won't be printing to the standard output. We'll be writing to the response writer. We've defined the handler function, and then we need to, if we want to properly implement it using all of the service wither idioms, we should have a listener. Lis would be wither.listener. And that's where, instead of calling here the sempiternal listen and serve, we will call directly serve with our listener, app.lis, and nil for the second argument, I think. Okay, do I have all the pieces? Almost. I still need to return an error, so I think http.serve itself returns an error. Yes, so let's return this. Okay. Will it work this time as a web server? No. Maybe I forgot to run wither generate. That's because if I change anything to the structure of the app or of the definition of the components, like adding a listener, yes, I will have to run again wither generate for code generation. Okay. I see that the error message is pretty nice to tell me, oh, you just forgot to run wither generate. Yes, I did. Thank you. That's kind of passive-aggressive, but thank you. Oh, that looks good. Allow incoming connection. Yes, I do allow. And that's why I have a second console here. I can call that with curl. So curl localhost 8080, and I will pass a string that will be adjulela. Okay. No matches found. Okay, maybe I'm in ZSH because of GNU something. I don't have bash anymore. Okay, still doesn't work. Port 8080 couldn't connect to server. I will need to ask my wither environment that is running locally. That's where I'm using the wither command, wither single status, what is currently running on my laptop. And it says I have a deployment, I have one component, and I'm listening to port something, something, something. Okay, let's try again curl with this port. Do you think it would work out of the box? I have my doubts, but let's see. Pressure. Adjulela reversed is hallelujah, hallelujah. Thank you. Amazing audience, very kind. Okay, now let's, it's nice to be running on my laptop, but of course it's better if we can actually deploy the microservices distributed application for cloud to the cloud. So because I get paid by Google, I will be deploying to Google Cloud and let you see how easily it's done and how easily you can do it at home. Let's see. I have a Google Cloud account and a project that is called Wither Demo Nantes with a nice project ID, Wither Demo Nantes. And I have the gcloud command line already installed on my laptop and already set up with this authentication and this project name. Let's see, gcloud config list. Yes, I have an account, I am properly authenticated, and I'm set up with a project Wither Demo Nantes. So everything I will be doing from this command line should end up in this web console. Cool. In order to deploy to GKE, I actually have to write a tiny config, aforementioned, the wither.toml. Let's do this. In the weaver.toml, I will have only two sections. One would be the name of the executable, the name of the binary. Still have 11 minutes left. We can do it, I think. And the other section is specifically to deploying to Google Kubernetes Engine. I will have to specify in which regions. Let's say US West 1, that's the name of a region in GCP. And I will have to write another thing, I forget, the listeners. List is the name of the struct field of type listener inside the app that I have coded earlier. So what does it say? It says public hostname. Normally, when deploying a $1 billion app to the cloud, we should do our homework and purchase a domain name. Here, I will just pretend I have the domain name reverser.com. I don't, but don't tell anyone. Okay, that should be enough to deploy to GKE. Let's call Weaver GKE deploy, and as a parameter our toml file. That should be enough and do all the required magic. No, why not? Cannot read listeners from binary. Oh yes. I want to emphasize that if I use Go Run on my Mac, obviously it compiles and runs my application. Yes, it works. If I build it, it will produce a binary executable that is called by default like my module, I think, so reverser. Yes, it works. It's not. Where is the pop-up that asks me to allow incoming connection? Okay, never mind. However, this binary is compiled for M1 max, so for some ARM architecture. If I want to deploy to GKE, it will actually try to deploy a Linux container. So I should compile for Linux. And that's what I'm going to do right now, cross-compilation. AMD 64, that's what it's expecting. Okay, so it successfully compiled a binary file reverser, and if I try to run reverser, will it work? Of course not, because it's not the same architecture. Okay, but now I should be able to deploy that to GKE. Are you sure you want to proceed? Yes? Okay. This is where it will take anywhere between 2 minutes and 10 minutes. And maybe we don't have that much time, so I will cheat and show you the end result. In the end result that I prepared in my rehearsal, it says at the end of this command, okay, everything worked fine, and now you have a cluster that is running at this IP. If I switch back to the console, in GKE, I did not have any cluster before the demo. Here I have a cluster being deployed right now. But if I switch to the other project where I've already been doing that in advance, I have a properly deployed cluster and an IP address. And so I can curl it and reverse the string for even more fun and profit. Let's try this. I will copy and paste the IP of my cluster. Maybe this will not work fault filter abort because I have to cheat and pretend I do have the host reverser.com. Will it work? Hallelujah. Yes, it worked. So that is proof. that with minimal config and with a little bit of code that can fit within 20 or 25 minutes of demo, we can deploy a distributed application to GKE that we've been writing from scratch using framework Service Weaver. So that's it for my presentation. That's it for my demo. I have a promotional slide. Where are my slides? If you are interested in Google Cloud, we have a shiny new Innovators program designed to provide you with a more personalized Google Cloud experience. You can join today by scanning this nice QR code. And if you have any questions about Service Weaver, most of them I will not be able to answer because I am not part of the software engineering team at Service Weaver. Some of them I will be able to answer because it's a very exciting young project that is, for now, Go-centric. In the future, it would be nice to add other languages, let's say Java maybe, Python, who knows, Rust, and also to write more custom deployers. I mean, it's already possible and easy to deploy to GKE or to deploy in a generic way to a Kubernetes cluster. We are already working on some more deployers to AWS, to Azure, etc. And I will be happy to discuss with you and to answer your question one-on-one downstage after the presentation. Thank you so much for having uploaded 3 times to my demo. Thank you. Also, during the preparation of this talk, we found 2 important bugs in the GKE deployers, and we fixed them. So that is thanks to the Service Weaver team of engineers, and thanks to me for discovering them, and above all, thanks to you, because all of this would not have happened without you. Thank you.